second half for today's conference. So before we give the stage to our speaker that I will introduce, let me remind you very briefly that the meeting is recorded and live streamed. So if you don't wish to be recorded, then let us know. So you need to keep the microphone and camera off during the talks. There is a live transcript function which will be active, and so if you want to know how to use it, then you can turn it off through clicking on the live transcript button on the bottom of the Zoom screen that you have. And final reminder is that we have the posters available all the time on Mural, and Costanza has just posted a link to Mural for everyone to use. This is where the posters will be for the rest of the conference. And so this is the little technical messages, and I'm glad to give the stage to our next speaker. So if Mariana wants to prepare the slide before I introduce her.
So have to unmute myself. Okay, I
Yes.
think now you can hear me, so I'm here.
We can hear you.
So thank you, Matteo. And now I will try second step to share my screen. So I hope that you
very good. Yes, so our next speaker, yes, is Mariana Haragus, speaking about transverse instability of periodic water waves, and the stage is yours.
Okay, so thank you, Matteo. And well, so my talk will be on periodic water waves today. So I'm going to consider the classical water wave problem. And I'll focus, actually, I restrict to gravity capillary waves. More precisely, I'll consider three-dimensional inviscid fluid layer. So here is a picture which is more nice than mathematical, and of fluid of constant density under the action of two forces, which are gravity and surface tension. And the flow will be irrotational. So I'm interested in periodic waves, which look a little bit like these ones. And in the question of transverse instability, I'll come to this a little bit later. So I consider here the full Euler equations, which are describing mathematically this classical hydrodynamic problem. So here are the equations. I won't insist too much on this because they may lead to, they are rather complicated, and I suppose all of you know these equations now. So there is, the unknown is the velocity potential, phi, here, and another unknown is the free surface in this water wave problem, which is eta here. I'm using in the equation here non-dimensional variables, so everything it's already written in dimensionless variables, so that there are only two parameters. So coming back to the equations, we have these two unknowns, eta and phi, velocity potential and free surface, and they satisfy these four equations. So inside the fluid domain, that you can imagine, it's a three-dimensional fluid domain with a flat bottom, which lies at y equals 0. So my coordinate systems is actually x and z horizontal coordinates, y it's a vertical coordinate. So inside this fluid domain, we have Laplace's equations, and then we have three boundary conditions, two kinematic boundary conditions, which are written here, and the Bernoulli boundary condition, which is written here. So I won't insist more than this. Just to say that all physical parameters which are arising in this problem, namely density, gravity, coefficient of surface tension, mean depth h, after taking dimensionless variables, compact can be reduced to two dimensionless parameters that I denote here, alpha and beta. So these are notations which arise quite often in the literature here. And these will be the two important parameters that which will also appear later in my talk. So these are the equations, and as I said, I'm interested in periodic waves, and when I'm saying this, these are periodic waves of these equations. So the full Euler equations describing what waves. Okay, so as it is well known, this problem has a very rich dynamics, so it has many interesting solutions, like Russell solitons, also periodic waves, more complicated structures. And also these equations and the problem has a lot of symmetries, several Hamiltonian structures. So we have all these rich dynamics, many symmetries and structures, and a lot of particular solutions. And among all these particular solutions, as I said, I will focus here on periodic waves. Now, mathematically, if we want to study this problem, there are, I can say, two main difficulties. The first one is that we have to deal with a variable domain. We have the free surface, which is unknown. You can see it on this picture here, which is, as I said, it's rather a nice picture than a mathematical one. So it's the function eta which describes this free surface, which is an unknown, and also the fact that on this free surface, we have nonlinear boundary conditions, which are these, the kinematic boundary condition here, and also the Bernoulli equation, which is written here. So these are, when we want to do rigorous analysis on this problem, these are two main difficulties. So as I said, I will focus here on periodic waves, and actually on two-dimensional periodic waves. So with a free surface, which is then one-dimensional, it is constant in one horizontal direction. And the question I want to discuss is that of their transverse linear instability. So the instability of these waves with respect to perturbations which are three-dimensional. I will only focus on analytical results, on linear instability, and as I said, on results for the Euler equations, but as predictions, I will also discuss some results for some long wave models. So first of all, the question of existence of periodic traveling waves, and here you also have a sketch of a solitary wave. So this is a question which was extensively studied in the literature. Well, let's say since at least Russell's discovery of the soliton. So here are some names of people, which this list, of course, is not at all exhaustive, and it's just to mention some contributions on existence of periodic waves and solitary waves. And the periodic waves I'm interested in this talk are actually periodic waves which exist in this blue shaded region here. So here is a plot in the parameter plane. Beta, it's here. This was one of the parameter, the one which is proportional with the coefficient of surface tension, and alpha was the second parameter. So remember, as I said, there are two-dimensional parameters. Here are these two parameters. And for instance, one class of results, of existence results, are found by using tools from bifurcation theory and dynamical systems. And when doing there are three bifurcation curves, the dark blue curves here, where solutions bifurcate, and in particular where we can find solitary waves, not this one is, for instance, bifurcating here, or periodic waves. But anyway, in all this blue shaded region, one can show that by fixing a parameter alpha beta, there exists at least one family of periodic waves which have small amplitudes, so which bifurcate from the constant state. And these are the periodic waves I'm going to focus on. Now, as I said, the question is that of transverse linear instability of these waves. So this means I'm interested in perturbations which are three-dimensional. So this is the plot of my 2D periodic wave that I'm going to perturb not only in the longitudinal direction, which is here, but also in the transverse direction, which is here. And in fact, for the instability problem, I will restrict to perturbations in the transverse direction, which are periodic. This will be the perturbations I'm going to consider. And in the longitudinal direction, I will restrict to a particular class of perturbations, which are coperiodic perturbations. More precisely, these are perturbations of this periodic wave. Here is a 1D sketch, which are periodic with the same period as that of the wave. One can consider more general classes of perturbations, such as subharmonic perturbations, localized or bounded perturbations. But once we have found, let's say, the class of coperiodic perturbations is somehow the smallest class of perturbations one can consider for periodic waves. And once we have shown an instability result for such perturbations, then one can conclude on instability for the other classes of perturbations. So to resume this, the perturbations I'm going to consider will be coperiodic in this longitudinal direction and also periodic in the transverse direction. Now, as you have seen, as it is also well known, these Euler equations are rather difficult, mathematically difficult, and it is technically difficult to investigate them. And very often, in order to get an idea about the dynamics of what should we expect on the solutions, one can get very good predictions actually using long wave models, in particular in these three shaded regions here, dark blue shaded regions here. And in all these regions, when we take the corresponding model equations there, it turns out that periodic waves are transversely linearly unstable for perturbations which are, as I said, coperiodic in X and periodic in Z, the transverse direction. So more precisely, perhaps the best understood region is the region here for parameter beta larger than 1/3, which corresponds actually to a regime of large surface tension. In this region, the model equation is the well-known KP1 equation, and there are several results on transverse instability of periodic waves, also spectral instability, linear instability, nonlinear instability for such perturbations. And there is also a result which is not so recent anymore for the Euler equations when we consider the periodic waves here. Now, if we move to this region here, again, in this region, one model, it's a version, an elliptic version of the focusing Davis-Stewartson equation. And in this case, again, there is a transverse instability result for periodic waves, and the same transverse instability in this region here, where we have as a model a fifth order KP equation. So this is a joint work with Eric Vallen in 2017. And actually, the talk today, it's somehow the continuation of that work. Once we have done this, the question was, well, what can we do for the Euler equation? It's just that it took several years before coming up to this problem. And the purpose is to show that we will have the same transverse linear instability results for the Euler equations. And it turns out that all these results that I mentioned here for the model equations, they can be found by a common approach. It is an abstract result obtained by Cyril Godet, a student of mine, some 5 years ago, and which originates actually in a joint work, well, 20 years ago, a joint work with Mark Groves and Shu-Ming Sun, where we have studied transverse instability of solitary waves, not of periodic waves. So what is this common approach? So this approach actually allows you to recover all the transverse linear instability result that I showed you before. And it is this approach that we use then for the Euler equations. The idea of this approach is to reformulate the Euler equations in this form here as a dynamical system in which the evolutionary variable is not the time t, but is the transverse direction z here. So the horizontal transverse direction z. So it's what we also call transverse spatial dynamics, and it is the formulation that we used for solitary waves and is the one we are going to use for periodic waves as well. So first step, consider a system which is written in this abstract form, where D it's a linear operator, F it's a nonlinear map, and then the advantage of this formulation is that when we take a periodic wave like the two-dimensional periodic waves I've shown you, then such a periodic wave, it does not depend upon the transverse direction z, it only depends upon the longitudinal direction x, and it is then an equilibrium of this dynamical system. And in this formulation, we can say that the periodic waves is transversely linearly unstable. So following the usual linear instability, definition of linear instability, if the linearized system, so when we linearize this system at the periodic wave, possesses a solution which is exponentially growing in time. So we have an exponential lambda t here for some lambda, which is actually an unstable spectral value with positive real part. And v lambda, it's a bounded function, which depends upon the two horizontal coordinates, x and z. And it's bounded in both, so x and z. And of course, the type of function v lambda that we consider here gives us the type of perturbations for which the waves is unstable. In particular, in our case, we will consider v lambda to be periodic in both x and z. And then the general instability result, which is a quite simple instability criterion in this context, is that under the following three hypotheses, actually the first two hypotheses are the main ones. First one is that this system is reversible. Alternatively, we can consider a Hamiltonian system. So under the hypothesis that we have a reversible system here, And the main hypothesis that when we linearize around a periodic wave, you obtain a linear operator which possesses a pair of simple, purely imaginary eigenvalues. So this is all. Third hypothesis, it's a technical hypothesis. We need to have well-defined operators. So D and L should be closed in some function space which determines the perturbations. So under these two main hypotheses, plus some technical thing, then the periodic wave U star is transversely linearly unstable. More precisely, there exists indeed a solution of the linearized system which grows exponentially in time, and such that V lambda is periodic in Z and belongs to our function space with respect to X. And this is the abstract result, which actually, as I said, allows to recover all the transverse linear instability results for the model equation. And also it allows to obtain transverse linear instability for the Euler equations. And this is actually joint work in progress with Eric Valen and his PhD student, Tien Truong. And what is the idea? The idea is, of course, well, we start with a formulation of the three-dimensional of the Euler equations as in this abstract instability criterion. I won't have time to insist much here. Actually, this is a Hamiltonian formulation for water waves. We have reversibility here as well. It's a formulation that we have used for solitary waves in the work I mentioned before with Mark and Shuming, and which was actually first found in a work by Mark Rose and Alexander Milke, again, 20 years ago, in a work where they discuss a slightly different problem. Actually, they discussed there the question of existence of three-dimensional water waves, which is another problem. So the difficulty with this formulation, when we want to use the abstract criterion for the Euler equation, is, of course, as I mentioned before, it comes from the boundary conditions, which are nonlinear, in particular when we are at the free surface. How to deal with these nonlinear boundary conditions? We learned this from this paper by Mark and Alexander Milke. So, and I, of course, keep all these technical things, and I focus on the transverse instability result for the Euler equation. So with Tien and Eric, we started to investigate this problem. We started actually with the dark blue region here. So fixing alpha and beta in this region here, our result shows that first, there is a one parameter family of periodic waves with small amplitude. One can compute expansions, Taylor expansions of these waves, which are actually needed for the arguments later. So we have explicit formulas of the leading order terms in these Taylor expansions. So we have these periodic waves, and the results, our result shows that all these periodic waves are linearly transversely unstable. The proof being based on the general criterion I mentioned before. So we consider the linearized system. So starting with this Hamiltonian formulation of the three-dimensional water wave problem. And then what we have to do, the main step is to check that the linear operator, which is obtained by linearizing around such a periodic waves, has indeed a pair of simple purely imaginary eigenvalues. The phase space we use here is actually a space of 2 pi periodic functions after normalizing the period of the periodic wave. So this corresponds to coperiodic perturbations. And the main task consists in showing the existence of these purely imaginary eigenvalues. Of course, the difficulty here is that, well, because it's, as usual, when we work with full Euler equations, we have rather intricate formulas, and it is rather technically difficult to study this operator here. I'll only say that we have a leading order part, which is the operator with constant coefficients that you can view as the linearization around the flat state. And then we have a perturbation, well, which looks quite discouraging at the beginning, but it is not so bad. You just have to be patient to handle all these terms. And which comes from the fact that we have linearized at the periodic wave. So this is the contribution in the linear operator, which comes from the periodic waves. And we have a linear operator, which is a matrix differential operator with periodic coefficients. So very briefly, how do we show the existence of this pair of simple eigenvalues? So the idea is to use a perturbation argument. We start from the fact that we can explicitly compute the spectrum of the leading order part of the constant coefficients part of the operator. And it turns out that this operator has only one purely imaginary eigenvalue, which is 0. The bad news is that it has algebraic multiplicity 6. So when you perturb such an eigenvalue, then you may have 6 eigenvalues moving around in the neighborhood of 0. But it turns out here that because of the different symmetries of the Euler equation, when we perturb this operator and we consider our linear problem, 4 of these eigenvalues will still stay in 0. And there are only 2 which move off the origin and they become purely imaginary. So this gives us precisely the pair of simple eigenvalues that we are looking for and proves then the main result, which is the transverse linear instability of these gravity capillary periodic waves in this region here. Now, as a final remark, this approach can, of course, be applied also in the remaining regions. It turns out, however, so if you want to go here, there are some additional technical difficulties. So in particular, in this region here, we have 2 parameter families of periodic waves. So the computations for this region are still in progress. And then if we are close to these bifurcation curves, then there are some additional eigenvalues which make the analysis more complicated. And I will stop here perhaps with a question. So far all these studies of transverse stability, instability of solitary also, but also periodic waves for gravity capillary water waves, in all these studies, it turns out that these waves are transversely unstable. So a question, are all these gravity capillary waves transversely unstable? And if so, is there a reason, a mechanical reason for this? Thank you.
Thank you very much. A really beautiful talk. So do we have questions? Anyone?
Can I ask a question?
Yes, of course.
Okay, so just to make sure, I have a really elementary question, just to understand. So your result, you consider finite depth fluid, right? No approximation of shallow water. Is that correct?
Yes, it's finite depth fluid, shallow water approximations where we can get along these bifurcation curves. So no shallow water.
So you use shallow water approximation?
No.
No.
No, because we are in this dark blue region here. So we really consider the full Euler equations.
And Hamiltonian formulation you were talking about, it's, I guess, Zakharov formulation, right?
Actually, no, it's a formulation due to Margros and Alexander Milke. So all operators are local. So it's really a dynamical system here in which U has 4 components actually. It's eta, the free surface, phi, the velocity potential, and then omega and psi are 2 additional variables that you can see as, well, roughly speaking, the z derivatives of eta and phi. So it's different than the Zakharov formulation.
So, and this is local just because you have more variables, because I mean,
because we want to keep derivatives to have differential operators.
Okay, thank you.
We have time for another very brief question, maybe.
I was wondering, could you please remind what is your epsilon? Maybe I missed it.
Okay. Epsilon, you can see it is the amplitude of the periodic waves.
Thank you.
It was here. Here. It's actually the amplitude of the wave. And alpha and beta are fixed. So I'm fixing alpha beta somewhere in this blue region, and epsilon is just the amplitude of the waves which bifurcate here.
Okay, so we have another question here, if that one is set. If one adds a current U, should one renormalize the alpha and beta parameters by changing the speed C to C plus minus U to get a new phase space diagram with the same instability criterion?
Sorry, could you say it again? I missed the beginning and I cannot see the chat.
Yeah, so if one adds a current U, should one renormalize the alpha and beta parameters by changing the speed C to C plus minus U to get a new phase space diagram with the same instability criterion?
I would guess so, but I'm not sure. It's a good question.
Okay, so I think that we can move to the next speaker. Thanks again, Mariana.
Thank you.
Yes, so our next speaker is Akis Athanasoulis, and he will talk about the Albert equation, bifurcation between Landau damping and rock waves. The stage is yours.
Great, thank you very much. It's a great pleasure to be here and give this talk. So thanks to the organizers for the kind invitation. So this is joint work with Maria Ptasnik, who is a mathematician like myself, and with Gerasimos Athanasoulis, Themistoklis Apsis, and Odin Gramstad, who are ocean engineers. So this is a project that is very much informed by realistic ocean waves, and we want as much as possible to see if we can drive the model towards being more applicable and more realistic. So I'm listing some papers here. Some are engineering papers. Most of what I'm going to be talking about today is the rigorous stuff, which is contained in this 2020 paper in kinetic and related models. Okay, so before I can state the Albert equation, I want to mention the 2 ingredients that make that it consists of. So the first is the NLS approximation, the nonlinear Schrödinger equation as an approximate equation for the envelope of water waves. So if you have your sea surface, a function of space and time, and maybe you have a characteristic wave number, characteristic wavelength, which gives us the wave number kappa 0. You can represent your sea surface through a complex envelope. So you plug this representation in the fluid dynamic equations, and then you get, as an asymptotic approximation, you can get a nonlinear Schrödinger. So focusing cubic nonlinear Schrödinger. In this talk, we're thinking unidirectional propagation. We have a wave system, we're going along its direction of propagation. And so this is an asymptotic model. It's clearly not perfect, doesn't have everything, but it is very widely used, and qualitatively it's kind of okay. So it's considered plausible in many situations. And to give some context here, the asymptotics, so this is not asymptotic in vanishingly small waves. The asymptotic parameter is slope, And slope doesn't get very large in ocean waves. So at the slope 0.13, the wave would break anyway. So second order error in slope means that this is a defensible model, this is a plausible model, even for relatively strong seas, so not vanishingly small waves. So that's a very widely used ingredient in ocean waves modeling. But there is a completely different kind of ingredient, which in fact is even more widely used in shipping, in design, when you want to compute 1,000-year wave in a location, and all these things that day-to-day engineers worry about. And this is a statistical point of view. And engineers know that if you take the statistics of your sea surface here now, or you go 1 kilometer to the north 20 minutes from now, you're going to find the same statistics, basically. So there is a very simple assumption that the sea state is, in an appropriate time and space scale, is stationary and homogeneous random process, which therefore you can work with through its autocorrelation or equivalently its power spectrum. And so there's a lot of know-how, a lot of expertise, and crucially, a lot of data from the field live in this universe down here, where you don't necessarily know too much about dynamics. It's mostly statistics. So the idea behind the Albert equation is, can we combine these two together and have a model with both of these key modeling approaches? And it's actually quite straightforward once you put everything together. This is due to Albert in his 1978 paper in the Proceedings of the Royal Society. So let's say we have an envelope describing our sea state. So we consider stochastic initial data. So it's a stochastic look at the sea state. And we want to work with the cross correlation. So we take a second moment in space. So we have now two space variables. And we take a second stochastic moment, and we want to derive an equation. What is the PDE that the cross correlation satisfies? And if we plug this in the equation, we get something. But of course, when you take moments of a nonlinear equation, you start with the second moment, and it brings out fourth order stochastic moments. And here we use the other crucial ingredient in the statistical modeling. Typically, ocean waves, if you need an assumption to go and work and get things done, you would assume that the sea state is a circularly symmetric mean zero Gaussian random process. So I'm not saying it is exactly those things. I'm saying it's a widely used assumption that is defensible in view of the empirical understanding and the data. So if you make this assumption, then for this kind of random processes, you have a complex Isserlis theorem that allows you to express fourth order stochastic moments through second order stochastic moments. And if you do this, now you have a closed equation for the cross correlation, having used the Gaussian closure. And moreover, you plug in this quasi-homogeneity. So we say, and moreover, this cross correlation, this random process is mostly stationary and homogeneous, and there is a small inhomogeneity. And by doing this, we leave enough flexibility in the model to include the data. So the autocorrelation here is the data that you get from the field, and there is room in your model for that. So that's very important. And now what you're solving for, the unknown function in this PDE now, is the inhomogeneity. So this is one formulation of the Albert equation, and qualitatively, the bifurcation in the title should be very clear now. So if you have these two assumptions, you go to this PDE, you have a small initial inhomogeneity. Is it going to grow to large localized events, or is it going to simply disperse and return to a homogeneous situation? So that's the bifurcation that you are interested in there. Okay, so now you have two space variables and the time variable. So it's not trivial what is the best frame of reference in which to work with your equation. So no point into spending too much time here. If you are not familiar with this kind of thing, this is just, it looks very complicated, I know. So the main idea is you do some change of variables, you do some Fourier transforms, and you go to a formulation where instead of two space variables, you have two wave number variables. So you have time and two wave number variables. So this I call the Albert Fourier equation, since it's Fourier transforming both variables, let's say. And I want now to take a very quick look and see what are the main actors here, what is going on here. So you have this first part, which is free space. So if everything else was zero, what this is trying to express is that inhomogeneity is traveling with its group velocity. This is easy, this we know everything about. So little f, the unknown function f, is the inhomogeneity in this new system of coordinates. Capital P is the power spectrum, so the Fourier transform of the autocorrelation. And here this blue term shows how does the background power spectrum interact with inhomogeneity. And this is the term that's going to decide, is this infinite energy solution feeding the inhomogeneity and making it grow or not? So the way it interacts is through this position density. So technically it's the inverse Fourier transform of the position density check. I'm going to call it position density just for brevity. And what the position density is the marginal of the inhomogeneity in the second wave number variable. And the way to think about it heuristically is this guy is measuring how inhomogeneous is my solution at wave number capital X. If I was tuning in wave number capital X, would I see a lot of inhomogeneity or a little inhomogeneity? This is what this guy is measuring. And so this is a key difficulty, let's say, the fact that you have this marginal is a key particularity of this problem. So that's how the spectrum interacts with inhomogeneity. It interacts with the position density. And you have, of course, the nonlinear term, the self-interaction, where the inhomogeneity interacts with the position density interacts with homogeneity itself. And you would have to initialize. So I'm not going to go into this right now. It will become apparent what happens with initial data. But if you think of a Cauchy problem, you would have to initialize as well. So the idea here is, let's put aside the self-interaction. So, okay, if we have a small inhomogeneity, the self-interaction is going to be small. So formally, that's why we have this epsilon here. If this small inhomogeneity is going to grow, initially it's going to be driven by this term. So let's linearize. Let's look at this linear equation and see what this is doing. So here, I'm just rewriting the linearized equation. Everything else is the same as before. And from now on, N and F refer to the solutions of the linearized equation. So if you bring this in mild form, okay, this is standard mild form. You are comparing with the free space solution. So free space, I mean, if there was no background spectrum, which you could solve explicitly, and you get this mild form. And the observation here is that you can integrate this equation in the little k variable. If I integrate in the little k variable here, I get the marginal, the position density. That's good. If I integrate this guy, this is the exact free space solution, I get the free space position density, right? What the position density would have been if I was only dealing with free space, no background spectrum. And on the right-hand side, you only have the position density and known stuff. So you integrate in little k, you get some integral kernel here, which is known. That's all that we care about. So you end up with this Volterra integral equation of the second kind. And now you can take a Laplace transform and solve it. So I'm passing now to the tildes. By putting tildes on top of my objects, it means I'm taking Laplace transform. So from time domain t, I go to Laplace domain omega. And so the Laplace transform of a position density can be expressed in terms of known stuff. And I can solve this equation for n tilde, and I can get this neat expression here. The position density on the Laplace domain is some transfer function times the position density for free space. Okay, so heuristically, formally, here we know what's going on, right? We know, assume everything is nice. So if this transfer function does not have poles on the right half plane, I can invert and I can put my inversion contour on the imaginary axis, and I'm going to get a nice modification of the free space problem, which is not growing in time. So, and this gives us a very clear idea for what the stability condition should be. It should be that this denominator doesn't get too close to zero. So this, so that's where it comes from. And you need to have a threshold kappa, so it doesn't go closer to zero than kappa for every wave number x and every frequency of the open right half plane. If this works, I would be able to go back and forth between Laplace and time domain, and hopefully this will be enough, to solve explicitly and do everything I need to do. Of course, this is tricky. This is starting to become analogous to the Landau damping problem for Vlasov equations. There are difficulties that I'm going to go over a little bit. And so this is not as simple as it sounds, but we'll see that in a second. And on the other hand, the simplest way to violate this condition is to have solutions of the equation h tilde of x star omega star equals 1. So in that case, the wave number x star is unstable, and the real and imaginary part of omega star is going to control how fast it grows and what is its group velocity. And in fact, if you knew the solutions to this equation, you could guess quite a bit about how this unstable structure is growing in the beginning. Okay, so now I want to discuss a little bit the rigorous result about Landau dumping, how we take this heuristic result from here and try to fill in the gaps and do it properly. So I'm going to talk a little bit about this and then how we apply this in a more hands-on applied context. Okay, so first of all, we need to create a well-posedness theory for the Albert equation. One did not exist in the literature. It's a funny kind of PD. It's not quite Strendinger. It's not quite Vlasov. You need to invent a little bit some new tools. So the key trick here is L1 norm for the Albert Fourier equation is very good because you control your inhomogeneity, and because you also have its marginal, the L1 of the inhomogeneity also controls the L1 of the marginal. And it turns out that you can work with your operators with the L1 norm. So you get a well-posedness result in the L1 norm, and then we have all the regularity. If the initial data is regular enough, your solution is regular, time derivatives are regular. So okay, so you have regularity. If initially you have regularity, you can have a lot of regularity. So now let me go to the precise statement of the Landau damping result and the idea of the proof. So here I am showing the linearized equation, but this is now in k and little x variables. So one wave number, one space. So it's one of the other formulations that I just flashed before. So it's just in different coordinates. You can think of it as the linearized equation in different coordinates. And the assumption is only that the initial data is regular enough in terms of derivatives and decay. It has a strong polynomial decay, something like that. And then the conclusion is that the L2 space-time norm of the spatial derivative of the position density is finite. So heuristically, this means that the spatial derivative of the position density goes to 0 for large time. In other words, the position density becomes flat for large time. So in large time, there are no localized events. So you start with some inhomogeneity and you end up in a homogeneous solution, no inhomogeneous events. And in fact, you can construct wave operators. We can say a bit more about the dynamics. Okay, but that's a bit of a detail. So the difference here, before the difference, the setup and the proof is quite analogous to the paper by Bedrosian, Mahmoudi, and Mo of 2018 in CPAM, where they have a Vlasov equation in infinite space. But the difference is here, we don't need a mean zero assumption for the initial data. This is somewhat significant in ocean waves, because if you have a homogeneous solution and a mean zero inhomogeneity, all this is allowed to do is to take energy from here and put it there. So it's okay, it's not fully homogeneous, but you would not be allowed, if you had the mean zero requirement, you would not be allowed to say, this is a homogeneous solution with infinite energy. This is a localized solution with non-zero energy, and they are interacting, and what happens then? You would be excluding that. So in this result, we are not excluding that. And let's go very quickly to give you the idea of the proof. So I showed you before this neat expression, the Laplace domain. You should not try to invert that. Instead, you should play around and try to Laplace invert this expression. So this is free space. This we know how to invert just by definition. We know this. This is what we're looking for. So here we have a different transfer function. That's the point. So, okay, let's try to invert this right-hand side. Then we know that on the open right half plane, everything is okay. So we put our inversion contour at real part equals delta. We write down the integral and we are left with a small exponential growth e to the delta t. So can delta be equal to 0? No, we'll see in a second why. Can delta tend to 0, and can we justify delta tending to 0? Okay, so why can delta not just be equal to 0? Because these objects, n tilde f as well as h tilde, in fact, are rescaled Hilbert transforms. And we have a frequency omega. Our omega is going to be delta plus is. S goes from minus infinity to infinity. Delta is small, so have a small real part, but the rescaling is such that we divide by I. So the real numbers here are not so important. I divide by I, it means I'm evaluating a Hilbert transform on a complex number with small imaginary part. And what happens if you take a Hilbert transform of any function and you go and evaluate it at a small imaginary part, you have your Sochowski-Plemeli formula, and the real axis then is you have a discontinuity across the real axis, right? So it's not a regular point. So if we go back here where we're divided by I, the imaginary axis in our problem is a singular area. So you cannot go on there. You have to approach using the Sochowski-Plemeli controls the limit. So the limit is the Hilbert transform minus I times the function itself, which altogether is often called the signal transform. And just to define the notation I'm going to be using from now on, dxp, I'm calling the divided difference of the spectrum with increment x. So if I take this expression and divide by x, that would be dxp. I'm going to be using that shorthand. So, okay, so we want to take delta equal to 0. We know how to take the limit from our Hilbert transforms, but the question is, are we allowed to pull the limit outside? And the most fundamental problem here is this an absolutely summable integral? Can I use my Lebesgue theory? And that's highly non-trivial because you have these objects in here, the signal transforms, which contain Hilbert transforms. And skipping some details, to do this, you would have to assert that you control the L1 norm of the Hilbert transform of the divided difference of the spectrum. And in general, as I'm sure, by now everybody are telling me, Agis, you don't control L1 norms of Hilbert transform. This is something that you don't have. And in general, you don't have, but in fact, we got lucky because there is actually one situation where it seems that you do have. So if you have a nice function of compact support, which happens to have integral 0, then its Hilbert transform is L1. And it's like a difficult exercise, right? So you can work it out. So you have this fact, which means, and we're talking about the divided difference of the spectrum. So if the spectrum of compact support is divided difference of compact support, and the divided difference of any function has integral 0 by construction, right? So we do have our absolute summability from this observation, and eventually this is the bottleneck there, and we're allowed to compute this inversion of the Laplace transform like that. And then this is what you bootstrap into the proof. And you show basically that the position density for the linearized problem behaves qualitatively the same way as the position density for the free space problem. So the presence of the spectrum does not really change the behavior of the problem. So we're very excited about this. And then we talk to our ocean engineer friends, and they're like, that's super, that's great, but the problem for them, they were aware of the Albert equation. The problem for them in deploying it is, how do I check your stability condition? Because, okay, we write this, but then, okay, I'm an engineer, I have a spectrum. How am I going to find out if this is true or not? And the simplest thing you can do is, okay, let's look for solutions. Is it violated? Let's look for solutions of h tilde of x and omega equals to 1. But if you remember that this is a complex valued equation and omega is complex valued, you have a nonlinear system of 2 equations in 3 unknowns, and you want to guarantee the existence or not of solutions for that. So this is not something, you open a book and you find. This is highly non-trivial. So the other theorem in our KRM paper, okay, so excuse this, it looks much more complicated than it really is. Let me just go to the idea real quickly. So if you give me a spectrum, you have a stability condition. An equivalent formulation of the stability condition is, you give me a spectrum P, I take for every wave number x, I take its divided difference with increment x, and I compute the signal transform, which is a complex valued function, and I plot this for all evaluated embedded variable. This gives me a curve in the complex plane, a closed curve in the complex plane. I do this for all wave numbers. If by doing this, I enclose a target real number, then my problem is unstable. If I do this for all wave numbers x and I don't enclose the real number ever, then my problem is stable. And this is not that difficult, because if you are taking larger and larger wave numbers x, you are dividing by a very large increment, and all these lines shrink to 0. So what I'm trying to show here, this dimension is wave number, and this is how far out these curves go, the real part of these curves go you only need to check a bounded range of wave numbers, because from some point on, everything simply decays to zero. And this is something you can do. You write a script in MATLAB and you do this integral, you plot these lines. And now you have a practical and reliable tool that can tell you this spectrum does not have unstable wave numbers. This spectrum has this interval of unstable wave numbers. And so we went on to apply this to some commonly used spectra. So a parametric spectrum that ocean engineers use a lot is a Jones-Swap spectrum. So there is a formula. This is what it looks like. They have found that in many cases, power spectra in the ocean do look like this. And what we need to care about here is there are two parameters. Alpha is power, so you just multiply the whole thing by alpha, okay? And gamma is peakedness, so it is measuring how peaked the spectrum is or how broad. So here you see an example of a more peaked and a less peaked spectrum for different values of gamma. So other people had looked at, if I go to the alpha gamma plane for a Jones-Swap spectra, what is the stable region and the unstable region in terms of the Albert equation? So the red dust line is the one proposed by Riballet and others. The blue dust line is the one proposed by Odin-Kronstadt in 2017. And the black dust line is the one that we compute by working with these contours here. And these blue stars come from measurements. There is something called the North Atlantic scatter diagram, which is sea states measured over the North Atlantic throughout the year. And every blue star is a sea state that has been observed and has been fitted to a Jones-Swap spectrum. So of course, it's not going to be exactly a Jones-Swap spectrum, but they know, given the statistics, what's the best alpha and gamma to match the statistics. Empirically, that's okay, as engineers do, and they give us this diagram. And now every star has a little probability. So this could be, 2% likely, this could be 1 in 1,000 likely, and so on. So there are 100,000 sea states there, and we find, all three curves, as you see, they kind of qualitatively agree. But what we find here still is that the most extreme sea states observed, so the highest gamma and the highest alpha, it really go up against the boundary for modulation and stability and just leak a little bit in the unstable side. And the total probability for these states is 2 in 1,000 or something like that. So this is empirically correlates extremely well with the statistics that the engineers know about rogue waves. So at least 99% of the time, linear theory is fantastic. You don't have rogue waves, everything is nice, but rogue waves are far more common than linear theory would predict. These are not 1 in 10,000 year events. These are not 1 in 1,000 year events. They are much more common than that. And this is kind of capturing this and making more precise pre-existing work. So more recently, we wanted to look at non-parametric data. So now we're looking at the collection of 100 non-parametric spectra from the North Sea with Odin-Kronstadt. 10 of them were selected to be extremely steep sea states, plus 90 randomly selected. For non-parametric ones, the curves are a bit messier, but in principle, the game is the same. You plot the curves and you see whether they include the target or not. But now we can go a bit further. We can ask, okay, there is a binary characterization, is stable or unstable, but we can ask how close is it coming to being unstable. So for example, the spectrum, if you are trying to enclose this real number here to be unstable, you would say it has come something like halfway there, right? So its proximity to instability, it's something like 0.5. And if it was out here, it would be 0.9. And if it was down here, it would be 0.1. And why is this significant? Because if you think of how non-linear Landau damping results work, once you have linear Landau damping, you bootstrap this to prove non-linear Landau damping. But the non-linear result tells you that small enough inhomogeneities will disperse. It cannot guarantee large inhomogeneities, the non-linear result. So in other words, if you are barely stable, you have a much smaller tolerance for inhomogeneity before something unstable happens. So in that sense, it makes sense to ask, does this correlate to probability of extreme events, right? If you are closer to being unstable, does it behave in a more unstable way, in a measurable way? So what we did for each of these states, Odin has a high order spectral method without all of these assumptions and simplifications that we build in our NLS, without any moment closure, no Gaussianity. So he's doing Monte Carlo, several thousand, tens of thousands, initial conditions, let it run for something like 2-3 days in physical time. as if the sea was running for 2-3 days, its initial condition, and does statistics for the probability of extreme waves. So on the x-axis here, you see for each sea state, the probability of a wave that is 2.5 times the significant wave height. So a conventional, common definition for a rock wave is on this axis, and on this axis is proximity to instability. You see that some spectra are modulationally unstable, just a couple of them. They really have proximity to stability equal to 1. And we're seeing both of these quantities vary over 2 orders of magnitude, and we see some reasonable correlation. So it seems that indeed this measuring stability like this does seem to hold up against a Monte Carlo situation where we don't use as many assumptions. Okay, so let me go very quickly now. Another concern that is very compelling for us is a genuinely 2-dimensional situation. You have one wave system going like this, another wave system going like this. This is not 1D or anything like that. You need to work on 2D. You don't have a single NLS equation for that. But what you do have is a system of 2 coupled NLS type equations, and you can play the same game, take second moments, do Gaussian closures, do Laplace transforms, and derive an instability condition. So this is something that we are doing and seems that it can be done. And so this is something that we're very excited about because crossing seas are thought to be very important in, in the field, in realistic ocean waves. So, okay, if I can very quickly summarize, if I want, to send a message out to the world, there is this way of doing second order theory for NLS with stochastic initial data. It is inspired by ocean waves, and it is plausibly realistic, applicable to ocean waves, and it could be to other kinds of problems where the same kind of assumptions are plausible. It has a key feature of a bifurcation between a stable and unstable situation. And although I didn't go into any details, I want to mention that this kind of analysis can give us a lot of insight on the development of the unstable events as well. So in 2017, we had, just working formally with the unstable wave numbers, we had predicted some universal scalings, time and space scales for the emergence of extreme events. So we cannot predict their full nonlinear evolution, but we can predict how they start to appear. And a short time later, the Matthijs, Grafke, and Van den Eyden had this, very well-known paper in CNAS where they do Monte Carlo, no Gaussian closures, no nothing, and they detect a universal rock wave profile that looks very much like what we were talking about back then. So it seems there are many directions that you can go from here, and we're very excited to be in this. Okay, so with us, I'd like to thank everybody for your attention.
Thank you very much, Haragus. And we have time for some questions.
Can I ask a question?
Please.
Yeah.
So it's Benjamin. So thank you for the talk. So just a question. So when you look at these waves, these field equations, you take initial random data essentially to represent this initial condition, which is statistical. I mean, could you do some kind of a hydrodynamic approximation for the evolution of this random data and extract some something from that? I mean, is this something that people have looked at?
So when you say hydrodynamic, you mean not do NLS, but do some Navier-Stokes or something like that? Yeah, so
what I mean is take NLS, but take it as a dynamical system with fluctuating initial data, like a itself being a dynamical system, and then extract from it hydrodynamics by extracting the appropriate conserved quantities and making some approximation of the usual hydro approximation, from which in principle you can extract some large scale correlations and all that. But I don't know if this is sufficient for your purpose though.
Yeah, so I think that's a great question, but so I'm trying to bridge it now to try and rephrase it in the way that I am thinking about it. So from my point of view, the biggest limitation in rock waves research, let's say, now oceanic rock waves, right? The physical problem is the initialization. Because when you work with a deterministic model, let's say, you are going to find whatever you put in the initial conditions. That's what you're going to find.
Yeah. Mm-hmm.
So the name of the game is how can you make your initial conditions as reasonably physical as possible, right?
Mm-hmm.
So, and the nice feature of this scheme is that eventually it does not depend on the initial condition. So that was a little bit lost. I was trying to go over everything a bit fast, but whether you are stable or unstable depends only on the spectrum, not on the initial data.
Mm-hmm.
And so to me, this is very important because you don't know the initial data here would be the imperfection in the homogeneity, right? You don't know this. And maybe somebody can tell me that with dedicated radar resources, you could in principle find it out, but it's not something that is sitting around, in all the oceanographers' offices in the world. It's not like it's readily available in large quantities. That's what I'm saying. So the detailed inhomogeneity. So the good thing about this is the most widely available data that we have and the most robust data that we have is the power spectrum. So it brings everything back to the power spectrum and the details beyond that. So the initial data is essentially treated as noise, right? If there are unstable modes there, they are going to be excited by the noise. And you're going to see the unstable modes, which again depend on the spectrum only. So to me, I mean, of course, you need to know it's physical. You need to know, does it have the right kind of conservation, which broadly has, not perfect, not everything, but broadly is physical enough. But to me, a big part of this is to try and do our modeling in a way that we try to use as much data as possible and try not to, prejudice the outcome, right? Because if we're too deterministic, I came from a semi-classical background. We do WKB and coherent states. But if you put coherent states, you're going to find coherent states.
Yeah.
You see what I mean? If you are too deterministic and too rigid in your modeling, you are most likely not really modeling the ocean. So that's, I don't know if it's coming close to an answer to your question.
Yeah, I can kind of. So basically, the initial distribution is actually not true. I mean, you have to measure it. So it's not it's not just, you cannot just make some kind of hydrodynamic approximation or some maximal entropy approximation somehow.
You can try to recreate specific scenario, right? But if you again, in the oceanic rock waves, you're thinking of a storm in the ocean. So I don't know how. So the best way I know of how to represent a storm is through its power spectrum. And my ocean engineer friends, I mean, there are people that will tell you there are these kinds of effects that you could put in, and maybe there is a current and this at an angle that you should try and put. Of course, there are things you can try and put in.
Yeah.
But in the open, that's the other thing. In the open ocean, you don't have bathymetry. You don't have. So a lot of things are taken away, and you just have the mixing of waves.
Yeah.
So to me, I want to bring it back to data. I want to use available data or measurable things, let's say, and try to go away from cooking up a model that is a little bit made up according to what I want to find,
Thank you.
Okay, so do we have other questions? Comments? Okay, well, if not, then I would thank Achis once more. Thank you again. And so we are now getting to